This video is the continuation on the use of organometallic reagents in the organic synthesis, and in this subtopic we are going to discuss on the organocopper 1, which usually reactions of organolithium compounds with copper 1 halides will give organocopper series, such as example here. So the first one is the RCU. So this is what we call a simple alkyl copper, and it is sparingly soluble in organic solvent. And another types of organocopper compound is R2 copper lithium. So this R2 copper lithium is very useful in organic synthesis because it is soluble in organic solvents, for example, ethers. As you all have learned before, in organic synthesis, usually we use organic solvent to facilitate the reactions. So in this case, if a compound used is soluble in organic solvent, then it would be a better choice to be used for organic synthesis. If we look at the first compound here, if we have organocopper 1, so what will happen when we have organocopper compound here? So when we react with alkyl halide, in this case is iodoalkane. So what we can see is we can produce a longer chain compound with the R group replacing the iodine. Okay, in this case, when we have this copper lithium compound here, copper lithium, so when we react with an alkyl halide, so in this case we do notice that there is double bond here, but the main important thing is that we have this halide, or we have this halogen. When we react this compound with alkyl halide, so what we get is that this bromine is now replaced by one of the R group, which is CH3 here. And the displacement of halogen, this is particularly facile, meaning it is easily replaced even when the halogen is in a position that is normally considered unreactive towards nucleophile. So this is why this organocopper is more feasible in organic synthesis, because it can even facilitate the reaction although the halogen is positioned at the unfavored position. The coupling of two organometallic molecules to produce the R2 copper lithium in the previous slide, it produces a larger molecule of defined structure. And if we have different types of R group, both aryl and vinyl organometallics are also effective in the reaction. And this coupling of lithium dialkyl copper molecules, it proceeds through trialkyl copper intermediate. Okay, let's take a look at example of a reaction here. Okay, the first reaction is when we have trans 1 iodo 1 nonene. Okay, we have alkyl halide here, and then we have these lithium dialkyl copper molecules. Okay, what happened is that if we carried out a reaction, one of the alkyl group here will replace the iodide. Okay, so we will get a longer compound with organocopper and lithium iodide. At the second reaction here, when we have iodobenzene, we have the iodide here, and then when we react with lithium dialkyl copper molecules, So what we get is one of the alkyl group here will replace the iodide, which will give us toluene, organocopper compound, and also lithium iodide. These are some of the examples where this organocopper lithium compound can be used in the synthesis of various compounds. And normally, if you look at this example, all of them involve the formation of new carbon-carbon bond. Okay, when we look at the example number 1 here, we have this copper lithium organocopper lithium compound. When we react with CH3X or R prime CH2X, what we will get is new alkane. New alkane, which this R group, the blue one, comes from the organocopper compound, while the purple one here comes from the alkyl halide that we use. Okay, if you look at this example, we have a cyclic compound, but it is not aromatic. And then when we react with organocopper lithium, what we get is this X will be replaced by R group. And then another example, if we use aromatic group, so this X is still replaced by R, and even if we use alkene group, the X is also replaced by R. Okay, if you look at example number 2, if we have cyclohexane iodide here, cyclohexyl iodocyclohexane. So what we get is we have copper lithium, dimethyl copper lithium. So in ether, it will give us methyl cyclohexane, where this iodide is now replaced by CH3 or methyl group. Then if we look at example number 3 here, first we have this organolithium. First we have iodomethane here, and then in order to form organolithium, we react with lithium metal in ether, so it will give us organolithium. And then this organolithium is then reacted with copper iodide, which will give us dimethyl copper lithium compound, and then this dimethyl copper lithium compound and then reacted to iodopentane. So this iodide is now replaced by CH3 to give us hexane. So this proves that this organocopper compound can be used in the formation of a longer chain alkane. Okay, another example of organometallic reagent is organozinc. Organozinc is not used much these days because it is less nucleophilic compared to a Grignard reagent, organolithium, and organocopper reagent. But sometimes it might be useful because it is very selective. An example of the use of organozinc can be shown in Reformatsky reaction as drawn here. Okay, when we have alpha haloester, meaning we have this ester and we have this halogen group, when we react to zinc metal, it will give us Reformatsky zinc enolates, which is the organozinc compound. So this is the organozinc compound. So this organozinc compound, when we react with aldehyde or ketone, what happens? It will form a complex with the ketone, and then in the presence of H+, this compound will be turned into beta hydroxy ester. Another example of organometallic reagent is organocadmium. Similar to organozinc, organocadmium also less favorable to use because it is less nucleophilic. Then Grignard reagent, organocopper and organolithium, but these organocadmium are often used to convert acid chlorides into ketone. For example, if we have a Grignard reagent here, when we react with cadmium chloride, it will give us organocadmium compound. So this organocadmium compound can be reacted with acid chloride to give us ketone, like drawn here.